All right, so it was interesting on the inverse exponential function how we weren't really able to come up with an equation in y=4 form. But we know it does have an inverse, so we don't know how to write the equation yet in the y=4 form. Since exponential functions are useful for modeling everyday situations, the inverse of an exponential function is also important. We're going to use y=3 to the x as an example. So our b, or our base, is 3. Even though we may not know how to write the equation of the inverse function of y=3 to the x in y= form, we already know a lot about it. So first, it wants to make a table for the inverse of y=3 to the x. Before we make the table for the inverse here, let's make a table for the original. Let's pick some negative and positive values. So let's do -3, -2, -1, 0, and then 1, 2, 3. So if I'm plugging -3 in for y=3 to the x, then we know that we'd have 3 to the -3rd power. 3 to the -3rd power is the same as if we had 1/3 to the +3 power, which is the same as 1/3 to the 3rd power is 27. So we know 3 to the -3rd is the same as 1/27. We can do the same thing with -2. 3 to the -2nd power is the same as 1/3 to the +2 power, and that's the same as 1/9. 3 to the -1st power is the same as 1/3 to the +1 power, which is the same as just 1/3. 3 to the 0 is just 1, because anything raised to the 0 power is 1. That's an exponent property, and if you're having a hard time remembering some of these exponent properties, you can refer back to our Math 1 video where we talked about that. 3 to the 1st power is just 3. 3 squared is 9, and 3 to the 3rd power is 27.
So we know that the inverse is the opposite. So our x values become our y values, and our y values become our x values. So I'm just going to copy this list over to the right spot. 1/27 and -3, 1/9 and -2, 1/3 and -1, 1 and 0, 3 and 1, 9 and 2, and 27 and 3. And there's my inverse table.
Part B says, if the input for the inverse function is 81, what is the output? Explain your reasoning. So if we look at our input, we see we don't have 81, but if we did 3 to the 4th power, or 27 times 3, that is 81. So we could say 81 would give us an output here of 4. So we can say that if our input for our inverse function is 81, we know our output is 4. And why? Because 3 to the 4th power is 81. So here we can see what we get out after we raise it to the 3rd power, and then our y values here are the different exponents we would raise 3 to get that x value. Part C says, using your answers from part A and B, if you put any number in for x into the inverse function, how would you describe the output? So if we were to write the equation, we know our x and y are flipped, so we would say x equals 3 to the y power. If I input a number in for x, I will get out what exponent I need to raise 3 to in order to get that x value.
Okay, so any number that we put in for x in this equation, we're going to get the value that we need to raise 3 to.
Or in other words, the output is the exponent of 3 needed to get that input for x. Let's talk about an ancient puzzle. All right, parts A through F below are similar to the puzzle that is more than 2,100 years old. Mathematicians first created the puzzle in ancient India in the 2nd century BCE. More recently, about 700 years ago, Muslim mathematicians created the first tables allowing them to locate answers to this type of puzzle quickly. Tables similar to them appeared in school math books until recently. Here are some clues to help you figure out how the puzzle works. Here we have this word log. Log base 2 of 8 equals 3. Log base 5 of 25 equals 2. Log base 3 of 27 equals 3. And log base 10 of 10,000 is 4.
Okay, so if I look at these, I'm trying to decide, how does this work? How does log base 2 of 8 equal 3? So I'm going to think through some processes. Well, 2 times 3 is 6, so that doesn't work. Oh, but if I do 2 to the 3rd power, that equals 8. So I know that 2 to the 3rd power equals 8, which helps me with that. So let's test that over here. I'm going to look at 5 to the 2nd power. Well, 5 squared is 25. So that worked for this one. And then 3 to the 3rd power equals 27. If I talk about 10 to the 4th power, that's 10 times 10 times 10 times 10. And if you put that in your calculator, it equals 10,000. So we found our pattern. So the base of our log raised to what our log equals gives us the value inside of our log.
If we want to use arrows to kind of show the pattern that Janice found, we would say we take our base here. So I take my 10, I raise it to whatever power my log is equal to, and then that equals my value on the inside. Here we would say 10 to the 4th is the same as 10,000. Now that we kind of know this pattern with this ancient puzzle, let's see if we can fill in some of these missing things here. So for part part A, we have log base 2 of 16 equals what? Well, I know with this ancient puzzle that my question mark is whatever exponent I need to raise my base to in order to get my answer inside my log. So 2 to some power is 16. I know 2 squared is 4, 2 cubed is 8, so I know that 2 to the 4th would have to give me 16. So that question mark would have to be 4.
All right, so if we look at D, it's saying the log base 5. So my 5 is here, and then it's raised to the power of 3. So in this case, it gave me what I was raising 5 to, and the question mark goes after my equal sign in this case. So 5 to the 3rd power. Well, 5 to the 2nd power is 25, and if I times it by 5 again, that would be 125. So our answer would be 5 to the 3rd power is 125. So that means that log base 5 of 125 equals 3.
All right, looking at part B here, we have log base 2 of 32. What does that equal? Well, I know that my log equals whatever exponent I need to raise that base to in order to get that inside number. So 2 to some power is equal to my inside of my log, which is 32. So 2 raised to what power is 32? I know that would have to be to the 5th power. So I know my answer would have to be 5.
Our next one is log base, we're not sure what that is, of 81 equals 4. So my question mark is going to be the number that I'm raising to a power of 4 in order to equal 81. So I need to know what number am I raising to the power of 4 to equal 81. So I know that 3 to the power of 4 equals 81. So my answer for this one is 3.
We're going over a lot of these problems because you'll see a lot of questions like this on derivative. All right, part C here, same idea. We have log base of something of 100 equals 2. So my base is unknown, but we know if we raise that to the 2nd power that we get 100. Something squared is 100, and we know that something has to equal 10 because we know 10 squared is 100. So we know that the base of this log would have to be 10 for this equation to be true.
Okay, our last example is log base 100 of 10 equals what? So my 100 is raised to the power of something, and that equals 10. Well, I know that if 100 is raised to a power and it equals 10, which is a smaller value, that means I'm going to have a fraction for my exponent. And looking here, I know that 10 to the 2nd power gives me 100. So I can kind of think of that backwards and know that if I raise 100 to 1/2, that I would equal 10. I'm going to say 100 to the 1/2 power equals 10. So my answer is 1/2.
If you're having a hard time with this, another way you could look at this is, since we know 10 squared is 100, we know that if we were to square root both sides, that's the same as saying 10 is equal to square root of 100. And so when you have square root, that inside number, that index, is always a 2. We normally just don't write it. And since it's 100 raised to the 1st power, this is the same as 100 to the 1/2, and that's the same as 10. 5-55 here says, how is the ancient puzzle that we just worked with related to the inverse function y equals 3 to the x that we did in the previous problem? Show how you can use the idea of the ancient puzzle to write an equation in y equals form for the inverse function y equals 3 to the x. So if we have our y equals 3 to the x, remember we can always swap our x and our y for our inverse. So if we swap our x and our y, now we have x equals 3 to the y. And before we didn't know how to write this in y equals form because we didn't have a method of getting a variable out of the exponent. But with this ancient puzzle, now we do. Now we can get our y out of our exponent with the logarithm. So if we do log and we have our base is where we raised our exponent to. So in this case, it's 3. So log base 3 of, and we know 3 raised to whatever power is equal to whatever's on the inside of our parentheses. So we know here we have 3 raised to the y power, so y is on the outside, equals whatever we got, which would be x. So our y equals form is log base 3 of x equals y. So y equals 3 to the x and log base 3 of x equals y. These are inverses of each other.